Cool. Hello, my name is Antero. I'm the lead developer at Wallscope, and I was asked to talk a bit about the power of machine learning. Well, I'm going to talk a bit about the power of machine learning. So at Wallscope, we have a vision of a world without barriers to knowledge. And we say that this is our vision, but what are we actually doing practically to achieve it? So we like to say that we build knowledge-enabled applications, and we say knowledge rather than data because there are a lot of software solutions, businesses, and even whole sectors focused on data. But we believe that data is not useful until you can understand what you want out of it. And that's what we usually call knowledge mapping, is where we basically ask the people who we work with to help us help them understand their data. Data in and of itself is only as useful as its quality, its context, and interpretation. So we go through a process of designing a solution alongside our clients where we want to understand the context, try to improve the quality of the data, and start conversations about machine learning and how we can use it to make sense of the raw data. Information is good, but it needs to be reasoned with if we want to act upon it. So through our experience of building linked data, we help capture information into our knowledge platform from which multiple applications can be built. This is our process, and throughout the years, it has evolved with us, and we have modernized our approach and our techniques, and we've refined them through working with different people to fulfill different use cases. And at some point, we turned to machine learning because we realized its potential, and also because, well, everyone was doing it. So that's what I'm going to try to talk about today. It's the so what, why does this matter to us, and especially to you? So let's define a few things first, starting with AI, which means artificial intelligence, if you ask any computer. Let's talk about it. Is it gonna kill us all? On the other hand, I think if I was a super intelligent AI, I wouldn't really announce myself. So it's not easy to define AI as one thing. In fact, I had a module at university on artificial intelligence, and this task was given to me and my peers, and I think the lecturer did that just to deliberately get us to argue with each other for 2 hours and prove that we're not that intelligent ourselves. So that being said, there's a definition I like that splits behavior into 4 categories, and any system can belong to one or more of these. And if it does, then you can technically call it an AI. So I'm just going to go over them. We've got thinking rationally, and that's can a system reason in a way that is rational / logical. So if this, then that. We've got thinking humanly. Can a system mimic the ways in which humans think? So for example, introspectively. Acting rationally, can a system act in a way that is based on the logical analysis of its environment? So if the temperature is above 21 degrees, then turn the heating off. And acting humanly, can a system act in a human way, usually to try to convince humans that it is a human? This is generally called the Turing test, or at least the Turing test is one way of measuring that. So we put a lot of emphasis on systems that can act humanly and fool us into thinking that they're human when we're measuring artificial intelligence. But in reality, that's a very hard task. And we're actually surrounded by a lot of systems that possess characteristics in some or all of the other 3 categories. And that's generally what we mean when we talk about artificial intelligence systems. It's systems that exhibit any combination of these types of behavior. So what about machine learning? The truth is that a lot of people use these terms interchangeably, and they're not really the same thing. A lot of the times when we're talking about AI, and intelligent systems, what's going on in the background is machine learning. So machine learning is basically when we have a lot of data and we use statistical models to try to find and exploit patterns in this data. This is said to be the learning part, and it's when a model learns from existing data to try to predict the outcome of something when seeing a new piece of data. So machine learning can be considered a subset of artificial intelligence, and great progress has been made in that field. Deep learning is also there. Let's not focus on that for now, but keep it in the back of your mind. I think it's going to become relevant because a lot of people are talking about deep learning as well. To understand the reasons why we've seen such an increase in the development of machine learning, it's interesting to look at the history of artificial intelligence as a whole to give some background and context. So AI has kind of a troubled past. The development of AI started out in the 1950s, and it promised to revolutionize the field of computing. People got excited with what could potentially be achieved. This is a period where we get most of the algorithms that we still use today in what I like to call algorithmic AI. This is the kind of artificial intelligence that it's easy to explain because it follows manually programmed procedures. And while it got us very far, and it paved the way to a lot of AI milestones like IBM's Deep Blue, beating Gary Kasparov in 1997, it didn't really fulfill the expectations at the time. So 1974 marks the start of what's called the first AI winter. And during this time, AI was still research, but not a lot because funding wasn't as widely available. And the field had become somewhat distrusted. Partly because of computing limitations. There's a pioneer in AI research, Hans Moravec, said, artificial intelligence requires computer power in the same way that aircraft require horsepower. Below a certain threshold, it's impossible. But as power increases, eventually it could become easy. And that's what we would see in the future. But it wasn't only computing. It was also because the expectations were too high. It's quite normal when there's a new field of research we don't know what we don't know. So the more we research, the more we realize that the problem is actually a lot more complex than it seemed initially. At the start of the 1980s, we had a bit of a resurgence in AI in the form of expert systems. And while these were useful, they showed little promise due to the work that it took not only to set them up and formalizing the knowledge behind them, but also to update and maintain them. So not really a comeback. In 1987, the bubble burst and we entered what's called the second AI winter. And there's a few springs and autumns, but I'm going to skip right to the next summer after that. So we're in 2011 and boom, big data. We've got big data. It's here to save us all. It's here to save AI and revolutionize the world. It's got to be the answer to all of our problems, right? Yeah, sure. So AI researchers realize that when you have a lot of data and computing power, a lot of the limitations of previous AI applications are not problems anymore. So we see a rise in algorithms that pick up patterns from masses of data. When big computers are coupled with big data, we get systems that can act humanly in ways that we had never seen before. Also, we know that the world is tired of experts, and that's also true for AI engineers because working with data is a lot easier than working with people. So ML models that work with data at scale can learn patterns about the world as we see it, about our languages and how we speak them, and even learn patterns of the psychology of how we act in specific situations like shopping, moving around a website, or even a city. And this is all well and good, but it doesn't come without its problems. So as fascinating and exciting as ML has been for data scientists over the past decade, the scale of it has exposed problems with these approaches. So models can pick up on patterns that we're not aware of, and they can work unexpectedly. For example, if we're training a dog-cat image classifier, and all of the dogs in our training set have brown fur, then we show the model a dog with white fur, and it might classify it as a cat. It's obvious for us that what makes a dog is not the color of the fur, but not for these models. They can also have hard to explain outputs. For example, if we're using machine learning in a credit decision system, when we're making decisions about lending someone money, we get an output, but not an explanation. So it could be a decision that carefully considers all the variables and all the risk, or it could be purely based on the fact that applicant name starts with an A, and previous data shows that people whose name starts with an A don't pay their bills on time, which is not true, by the way. And we'll never know that the decision was based on that. And finally, one of the biggest problems with machine learning is that we approach machines as these logical fact boxes, and we assume that algorithms cannot be biased and are impartial in a way that humans cannot be. So what we've been finding out is that actually when we have machines that are learning from humans who are biased and partial, we get models that are biased and partial. So think about the examples I used before. What if the dog versus cat example is a job application form that instead picks up on someone's skin color, or a loan application that rejects you based on your name is already pretty bad, but it might be easy to pick up when we start looking at the results. But what if we get a system that picks up on your postcode and makes decisions based on where you live? It might be harder to find and track, especially because it is kind of a well-known bias that we carry as humans. So humans looking at the results would just assume that the model is making these decisions based on the same factors that they would. Just as a last example, there's a predictive policing. With the trend in big data and machine learning, researchers started to look into how crime can be predicted by using data from previous crimes. And multiple studies have shown that the data that they were starting from was highly imbalanced, because there's more policing in neighborhoods that are deemed more dangerous. So this results in more crimes being reported, which doesn't necessarily mean that more crimes are committed. And this leads the model to predict crimes in those neighborhoods, because there's been more crime there in the past, which leads to more policing there, which leads to more crimes being reported, and it creates an endless feedback loop. So what can we do? Machine learning isn't really a one-size-fits-all solution, and it can be good at solving concrete problems, but as we've seen, more data sometimes just accentuates the problem, and we're left with the old adage that ML engineers have been using since the 15th century, garbage in, garbage out. So being aware of our biases and the biases in our data is good and necessary. But sometimes we need something more structured than explainable. Sometimes there's more on the line than you just being recommended a product that you're not interested in. So let's talk a bit about knowledge graphs and how they're here to rescue us. I'm going to try to keep this short. Knowledge graphs are a group of technologies and methodologies that can take many shapes and forms. And for the purposes of this presentation, we're just going to focus on linked data and RDF-based knowledge graphs, mainly because that's what we do and that's what we use. So RDF knowledge graphs are a way of structuring and organizing knowledge. We can define the shape of our data using ontologies, rules and reasoners, and we can even infer facts that are not stored. That's a very important point because it means that from a limited information, we can complete a picture. An example I like to use is there's a knowledge graph that has me and my sister as entities. It stores a fact that says that we're siblings. It also stores a fact linking me to my mother and my father. And finally, it stores a rule that says the two entities who are siblings have the same parents. And let's try to not complicate this with the step-sibling relationships because you don't want to listen to me speak for the rest of the day. So when we ask this knowledge graph who my sister's parents are, even though that information is not stored, it can be inferred, and that is very powerful. So a lot of companies use knowledge graphs in the background, things like Amazon Alexa, Google, among other things. But they don't really like to talk about that. It's almost as if they're scared of mentioning you know who. The reason for this is mainly because they got a bad reputation, knowledge graphs. They're seen as these obscure technologies that are hard to use for developers. Linked data and RDF are regarded as highly academic fields, and while research is good, it doesn't always translate into real world applications, or at least where it does, it doesn't have the visibility of other similar research-led fields. And finally, to be honest, knowledge graphs are kind of hard. It's hard to populate one because it requires structure, and it requires people to agree on a structure, and it requires data to be converted and so on. So looking at machine learning and knowledge graphs, what if there was a way of taking a hybrid approach where we can get the best of both worlds, where the shortcomings of one solution are mitigated by the other? Can we do that? And also, who wouldn't want that? So this can be done, and machine learning can be used to automatically populate a knowledge graph. It's one of the underpinning concepts in the product that we offer at Wallscope called Data Foundry, where basically we can take data, work with people to understand its structure, and then we can automate the process of turning data into a knowledge graph. So we're bringing structure into unstructured data. This is also what Google is essentially doing with web pages. So there's a lot of metadata that is provided in the form of RDF on web pages themselves, thanks to a project called schema.org. And that helps Google come up with those fancy cards you see on a web search. But they've moved past asking people what their page is about. And nowadays, Google can understand a lot more about web pages than what is provided by the author in the form of metadata. And the opposite is also true, where we can use knowledge graphs and knowledge representation to make the ML function easier. So the simplest example is data augmentation. So if we're training a model to classify text entities, for example, we might use training data like Bob Marley is a Jamaican singer. If we template this statement, we can automatically generate millions of statements like Kendrick Lamar is an American rapper, Bjork is an Icelandic singer. And this is all factually correct data that we can then use to train machine learning models. Another example is in simplifying models by putting the onus on the knowledge graph. If we break down complex models into simpler models, for example, the earlier cats and dogs classification problem, if we instead train models to recognize cat and dog features, like for example, cat eyes, shape of the head. And then we have an ontology that describes a cat as having vertical pupils, big whiskers. Then the model can output that an image is of a cat or of a dog with a degree of certainty based on individual features rather than an overall view. And this makes the ML models a lot more explainable, because when the model tells us that an image of a snake is a cat, it will tell us that it says that because of the vertical pupils, and then we can adjust our data and models accordingly. So I think that's probably enough. I've been talking for a while now. As a quick recap, we talked about AI and its brief history. We've seen that ML plus big data is cool. We've seen that ML plus big data plus the responsible developers is not cool. And we talked about knowledge graphs, what they are, and why we don't say RDF anymore. And finally, machine learning plus knowledge graphs is very cool. So are there any questions? I included some links throughout the presentation, and there's this flow.page/Wallscope, and you've got a lot of resources that I think might be useful.
Thanks, Antero. I would ask you if you could copy those links to the chat so anyone can click both the Medium link and this one. Okay. And again, if anyone has any questions, you can raise your hands. Oh, Emma is already copying it through. You have these links on the chat now, and don't forget to raise your hands for any questions. There's not any hands raised just yet. Oh, Antonia, go for it.
Yes, if I may. First of all, thank you very much for the presentation. I especially enjoyed the dive back into the history of AI and the many memes sprinkled throughout. I was wondering about, because I mean, I come from this research area that you kind of hit out a bit on, too academic sometimes, and I agree with that we're not focusing on real life problems enough at times. But one theme that's coming up more and more in research is around interpretable machine learning and interpretable AI. And I've seen that in different parts, such as support vector machines, neural networks, etc. So I just wanted to hear your thoughts about this general movement in academia towards this interpretable theme.
Yeah, I think it comes out of a necessity when you have big companies that are starting to finally have to answer for their technologies and what they're doing to the world. And don't get me wrong, what I said about the field being too academic. It's not that I think that it shouldn't be academic. It's just that I think that there's a lot that is not being transposed into outside of academia, and it's a shame, because these technologies are very useful and a lot of people are using them, but it's just we're not talking about it. About the explainable AI, I think that it's a necessity, and we will have to go there. It's just about figuring what the best way is. And I think that the more complex a model is, the harder it becomes to explain. Like when we go into deep learning and we have multiple layers, it becomes kind of hard to understand what these models are using as basis of their predictions. So my personal opinion is that we can look at supporting technologies like knowledge graphs, and we actually make the model simpler. We actually we reduce the size of the black box, and maybe we have 20 tiny black boxes, but we can kind of see what's going on in each of them. And then we have a supporting system. That being said, I still think it's useful to do any research that can go into explaining deep learning models and all of that, because the truth is not everyone is going to use knowledge graphs, and people are still going to use machine learning. So I think we need a mix of both.
Thank you so much. There's no harm done about the research community.
Again, if anyone has any other questions, do raise your hands. So Antero, I'll put you on the spot. So what's next? You talked about the history, you talked about what's working, what's not working. What would you say is coming next?
Is that a prompt to sell us?
Well, if you take it.
I think that it's what I was saying. Like machine learning is just not enough anymore, and we have to use these hybrid approaches, and we have to think about how other technologies can support the machine learning function to mitigate or at least attenuate the concerns of privacy, the concerns of data, and I personally think that knowledge graphs can do a lot towards that, because they can help with the explainability, they can help with augmenting data so you don't need to collect as much data about people. So I think that to summarize, the future is knowledge graphs, and we can already see that there's a lot of interest in the past 2 or 3 years. There's a lot of new tools, some people are actually not as afraid of talking about them anymore. We've got blogs from big companies like Google, eBay is developing their own knowledge graph database and things like this. So yeah, let's see. In the meantime, talk to us, because we do machine learning and knowledge graphs.
We have another question from Katie Guthrie.
Hi, yes, it's not so much a question as an observation, because in following up on Antonio's question there about interpretable and explainable AI, because that was the subject of a session I ran yesterday all about the need for explainable AI. And I was just going to mention the fact that at that session we had a presentation from Dr. Andy Starkey from Aberdeen University, and it's his specific research area around about explainability within AI. So I just wanted to mention that in case Antonio was interested in following up on it. And I actually had a question for Antonio that I didn't get in quick enough with my raised hand. If that's okay, I'm sorry. I'm sorry. It's the wrong presentation, but which was just about kind of the use of it then. So you've done the research, and then how is that going to feed into kind of making a difference or making changes, and what use you foresee for it, or what different uses you foresee for it?
Yeah, thank you very much for the question. I think that's a very good one, because it also kind of touches upon what Antero said. Research only goes so far, and we need people to actually act on it and actually use it in a way that is then benefiting the wider society, even if that sounds maybe too grand in this case. So what I'm doing from my perspective is I'm in conversation with the Scottish government. So I'm sharing my insights and what I'm working on with them. They have actually COVID network groups that are looking at the use of data during the pandemic. And so I'm sharing it with policymakers in that sense. And I hope that my findings can then inform wider decision-making, planning, and also just understanding what's happening right now in the very dire preparation of possibly second wave, possibly future pandemics, etc. So it's a lot about understanding what's happening now to be better prepared in the future.
Thank you. We have a question from Michael Donald. So you should be able to unmute yourself now, Michael.
Yeah, I've got here. It's a question for Antero, and I hope it makes sense. I'm struggling to bring this into the real world. So Antero, I think I met you possibly 3 years ago, first of all, and listening to you today, you have a much broader Scottish accent, which I think is fantastic. However, in relation to the 4 facets of AI that you were exploring and describing, what can we take, how can I sort of picture it in my own mind. It says, what aspects have you consciously or subconsciously used of those facets that your Scottish accent has become more pronounced?
Yeah, so like again, that definition of AI is one definition of AI, and I think it's very hard to define because, well, without wanting to get too philosophical, it's kind of hard to define intelligence, and it's kind of hard to define intelligence in the sense of humans and how humans are intelligent and other species and how they are intelligent. So when it comes to defining artificial intelligence, it's also we also have to define what intelligence is. So those four categories are just ways to look at current systems and systems that exist, and trying to think of what parts in those systems are intelligent. And I mentioned that lecture in AI that I had, and one of the questions that we were asked is, are self-checkout tills in supermarkets intelligent? Because they are kind of acting in a human way where they're actually replacing a person. So is that system intelligent? Do we consider that intelligence? So I don't know. I'm kind of going around the question and not answering it because I think it's really hard to answer. But yeah, here we are.
Can I maybe pick up on it a bit and say that I'm picturing that somehow over the past 3 years that your brain has been using a form of machine learning?
Well, not machine, because I'm
Okay.
still a human, I think. For now.
Okay.